Good morning. So here we have a problem that's been sent to me by a student. It's a type of problem that we would call an optimization problem, and it reads like so. The figure shows a rectangular field in which AB is 300 and BC is 1100 meters. So probably the first part before I even continue with the problem is just to label these sections. So AB being 300 meters and BC being 1100 meters. Part A, an athlete runs across the field from A to P at 4 meters per second. From the time taken to run, find the time taken to run from A to P in terms of theta. So what I would be doing with this question, part A, is I would set it up as a right angle triangle first up. So here I have my right angle triangle. I have theta. I know that 300 meters is that distance from A to B. And the distance that the runner would have to take from A to P would be a distance that I'm going to call D. Now, I can use my trig ratio. Here I have an adjacent and a hypotenuse. So I'm going to label it as cos theta equals the adjacent, 300 on D. And then I rearrange this expression in terms of D to give me 300 cos theta. Now, the question in part A is not looking for the distance. It's looking for the time taken. But they've also provided us with a velocity that the runner is moving at, or a speed that the runner is moving at. So what I'm going to use is V equals D on T, and I'm going to rearrange that in terms of time, and that's going to give me distance on the velocity or the speed of the runner. Therefore, what I can say is the time is going to equal the distance, which I know is 300 on cos theta, divided by the velocity or the speed of the runner. And I know that that's 4. Therefore, I find that my time is going to be 300 divided by 4. Okay, I could write that as 300 4 cos theta. And this gives me 75 all over cos theta. So that's the time that the runner takes to travel from A to P if the runner is cutting diagonally across the field. The next part, so part A is done. The next part is the athlete on reaching P immediately runs at 5 meters per second. It might be that the surface is more conducive to their running. So find the time taken to run from P to C in terms of theta. For this part of the question, part B, what I want to do, I'll just take that back. What I want to do is I want to draw the rectangle as it is, set up my triangle, theta, 300 meters. Okay, I know that that's my distance. I know that this distance along here is going to be 1100 meters. But within here, I'm going to have some distance x, which the runner is not traversing. And the leftover distance is going to be 1100 minus x. Okay, so I want to make note of that. And what we're really looking to find is this distance here. Now, I want to also then be able to say what x is going to be equal to. So if I use a triangle here, theta, 300, x, I don't have to worry about the distance. Here I have an opposite and an adjacent, therefore tan theta equals x on 300, and therefore x will equal 300 tan theta. And I'm going to apply this to this distance which I'm looking for from point P to point C. Okay. Therefore, the distance P to C is going to be given as 1100 minus 300 tan theta. Now, I also know that the velocity that the runner is taking is 5 meters per second, and I can use the time constraint. Time equals distance on V. So the time here is going to be 1100 minus 300 tan theta. And this is all divided by 5 because that's the speed of the runner. And my time would come out 220, 1100 divided by 5, minus 60 tan theta. And this would be the time to travel for the runner from point P to point C. All right. So that's part B. Part C then says, use the results from A and B to show the time taken t seconds is given by 220 plus 75 minus 60 sine theta on cos theta. Well, it sounds a little bit challenging, but the question is actually quite easy. What we want to be able to do to find the total time is to say time A to P plus time P to C. And we've already found those constraints. So we know that that's going to be 75 cos theta minus 220 minus, or plus, sorry, 220 minus 60 tan theta. Now, moving forward with this, what I might do is I might separate the terms just a little bit further and say 75 cos theta minus 60, and with this tan I'm going to do something a little tricky here. I'm going to say tan theta is equal to sine theta on cos theta. This allows me then to combine the terms, and I get 75 minus 60 sine theta all on cos theta. And I believe that's what they were looking for us to show, and that's been shown. Then in part D, what they're looking for is for us to find dt d theta. Okay, so when they're looking for us to find dt d theta, what we then need to do is we need to derive this term, and what we would be really deriving is, what is d theta. We can leave the 220 out. Sorry, I'll just clean up the sheet a little bit. Okay, and what we're looking for is 75 minus 60 sine theta on cos theta. Now, we have a quotient rule here. I would be suggesting you can do this a couple of ways. You can use your quotient rule, which I'm not going to do, but you could be plugging this into your computer or your calculator and then be able to resolve it to find what that derivative is. When you come to find the derivative, then part E, okay, would be saying, okay, find dt d theta. I'd be suggesting that you use your CAS to be able to find that, okay, and then substituting, and that will give you show the value of theta, which t is minimum. That's the optimization when the time is minimum. So the quickest time that the runner can get from point A to P to C, that's the quickest time that we can do. But what is theta for that time? And then substituting that back into this equation in part F, okay? Min to be able to find the minimum time. Okay, I hope that helps.